Hello guys, my name is Lazar and today we're going to be doing a LeetCode problem. This problem is called odd even linked list. Given the head of a singly linked list, group all the nodes with odd indices together, followed by the nodes with even indices, and return the reordered list. So already we know that we need to keep track of the indices of every node we see. The first node is considered odd, and the second node is even, and so on. So this is pretty obvious. First one, if it has in this index of 1, then it's obviously going to be odd. The second one is going to have an index of 2, so that's going to be even. This also tells us that we want to start counting at 1 and not at 0, because if we start counting at 0, then the first node would be even. But due to this sentence, we know we have to start counting at 1. Note that the relative order inside both the even and odd groups should remain as it was in the input. So, for example, in this first example, the correct answer is 13524. What this sentence is telling us that is we cannot return a linked list that is 15342 because in the beginning it was 2 followed by 4. So we cannot return linked list where the even section is 42. We need to maintain the relative order. And then finally, we must solve the problem with O of 1 extra space complexity and O of n time complexity. So here in the first example, we have 1, 2, 3, 4, and 5. Now the odds are going to be 1, 3, and 5. So let's put them in the first half of our answer linked list. And then the evens, let's put it in the second half. Which is why we have 1, 3, 5, and then 2, 4. Same thing goes for example 2. Here you can see that the first node, the value of the nodes doesn't really correspond with the index position. So we are going to want to have a separate variable keeping track of that. So here we have 2, 3, 6, and 7. Those are all the odds, so they go in the first half. And then the 1, 5, and 4 go in the second half. So let's get right into the drawing to see what we really need to solve this question. So I'm going to write down the first example. So we have 1, 2, 3, 4, and then 5. So the first thing we want to do is keep track of the proper heads. So for example, we know that the first node is the beginning of the odd. So let's just call that odd start. If I can write this nicely. There we go. And we know that that next node is going to be the beginning of the even. Now from here we want to do some rearranging. So we really want to be changing these pointers. So for example, let's say we're currently looking at 1. We want to hold in a temporary variable the next node the 1 points to. And then we want to change the pointer of 1 to point to next.next. In this case, 3. Now when we're iterating, we're going to be moving to 2 since we held this temporary variable. Let's now move to it. And let me get rid of that box. So now we're at 2, and we're going to want to do something extremely similar. We're going to want to change the pointer of 2. Well, of course, first we're going to have to hold its next node separately. But I'm not going to be drawing that box the whole time, so just keep in mind that we're always storing its next node before we change it. But after we store it, we do want to change what it points to. We want to look at next.next. In this case, it's 4. Now we move to 3, and we want to do something similar, point it to 5, next.next. And once we get to 4, we are pretty much done here. And the reason we're done is because although we do have to point 4 to null, to none, we can just stop here and rearrange what 4 is supposed to point at and also what 5 is supposed to point at. So since 4 is an even node, I'm gonna mark all the evens right here. I'll do it. It's weird. There we go. Okay, right there. And all the odds I'll do it in yellow. Right here. Perfect. Now since 4 is an even node, what we want to do is first change its pointer, make it look to nothing, make it point to none. And then this 5, well, before we made the change of to none, we first had to get this 5. And have this 5 point to the beginning of even start. So point to whatever even start is. In this case, I used to do a big arrow like this. That way, when we were to return this list, we're going to be returning odd start. So we're going to have 1. 1 points to 3. We're following this arrow right here. 3 points to 5. And then 5, since it was the last node, and that was an odd node, it's going to look at the even, at the first even node. Which is why we have to keep track of that even start node. So now 5 is going to point to 2, and then 2 is going to point to 4, and this is the correct answer. Now you might be asking yourself, okay, well, that makes perfect sense, but what if we didn't fall in that scenario, right? Oh, I'm losing all my dots. That's unfortunate. Let's say there was a 6 here. Let's say there was a 6 here. We could change this 4, make it look to the 6. And now we stop at this 5. But now we know this 5 is odd, is an odd number. We know the 6 is already pointing to null, which that's already correct. Since it's an even, it's the last even, we want that. So we don't really have to change much. All we really have to change is the pointer of this 5, and just make sure it looks at even start. So instead of changing 2 pointers, if we had finished on an even node, remember when we finished on the 4, we have to make sure 4 looked at none, and then 5 looked at even start. But if we finish on an odd node, all we have to change is the pointer of that node. So it's just one change instead of 2. Now if we were to return this, we'll be getting 1. 1 points to 3. 3 points to 5. 5 points to 2. 2 points to 4. And then 4 points to 6. And of course 6 points to nothing. And this is also the correct answer. And that's all we really have to do for this problem. Now, though we can keep track of knowing whether the last node we're on is even or odd by using that outside variable. That outside variable that I talked about in the beginning, we can call it position, or POS for position, and let's just set that equal to 1 in the beginning. And if next dot next is none, we know we have to do this operation and we have to look at what POS is. So let's get right into the programming and see if we can write this out. All right, perfect. So the root is going to be equal to head, and then even start is equal to head dot next. Now this right here might throw an error, because if we look at the number of nodes in the linked list, it is possible for the number of nodes to be 0. So it's possible for us to get an empty linked list. So for this to not throw us an error, we can just do a simple check in the beginning. If not head, return none. So there we go, and now everything's fine. Now let's create that POS, standing for position variable. And now let's do our while loop so we can iterate through the linked list. Now, while head and head.next. Now, why do we want to make sure that head.next is valid? Well, it's because we're going to be doing head.next.next. And if head was equal to none, then head.next, I'm sorry, if head was equal to 1 and then 1 points to none, then head.next.next would throw an error because none does not have an attribute called next. So we're just making sure we're not falling into any errors in this while loop by having that as the condition. Now we want to temporarily store the actual next node. Yes, how we did in the drawing. And now we want to do some computation. So if not temp.next, now keep in mind this temp.next is the exact same thing as head.next.next. So if not this, then we know we're in one of these scenarios where we're on this node and there's nothing after. So if that's the case, we want to look at what a precision is. If a precision is even, then let's change temp.next and make that equal to even start. And then also make head.next equal to none. Now, what is this saying? Well, this is saying the original problem we had. Let me see if I can go back. There we go. Head is currently right here. Temp is currently right here. And then temp.next is pointing at nothing. So if not temp.next and our position is even, in this case it is, position here will be 4, then temp.next is equal to even.start. Where is it? There we go. So temp.next is this, temp is 5, and .next, change that pointer, instead of looking at nothing, change that pointer and make it look to the start of even. And then head.next is equal to none, because since this is head, we want to remove this pointer that makes it point at 5, and let's just point it to none. Perfect. Else, if this is not the case, then we find that scenario how we had when we had the 6 in there, where head.next is equal to even start, and we only have to change one thing. Now, if we did fall inside of this condition, then we know we're basically done with our while loop, and we can just go ahead and break. Else, if that condition did not run, then what we want to do is just continue iterating normally. And by normally, I mean just make the next pointer point to the next. So what that is saying right here is how we had right here. Remember, we want to change the pointer from, instead of going to the next node, to go to the next. So we're doing this right there, that operation. And then finally, we want to continue iterating normally, so head is equal to temp. And then let's increment our position variable as well. And then finally, we can just return root. So let's run this, make sure it works. It does. Let's submit. It gets accepted. Perfect. So hopefully you guys were able to understand this problem now. And just to make sure that it has this complexity, we don't have any data structure where the size of that data structure increases depending on our input. So we did meet this all of one's extra space requirement. And we also have the all of n time complexity, because we just have one while loop that's going to be iterating over the linked list once. So again, hopefully this helped, and if it did, please leave a like and consider subscribing. And thank you guys for watching.